Good morning, students. Today we will discuss about perpetual motion machine of the first kind, or in short, we will call it as PMM1. Okay, the first law states the general principle of energy. Energy is neither created nor destroyed, but only gets transformed from one form to another form. We know this. There can be no machine which would continuously supply mechanical work without some other form of energy disappearing simultaneously. Such a fictitious machine or such an imaginary machine is called perpetual motion machine of the first kind, or PMM1 in brief. A PMM1 is thus impossible. You can see in the diagram here, you can see a machine here. Okay, this machine we will call it as PMM1 machine. So you can observe here, in this machine we are supplying heat to the machine and it continuously generating the work without some other form of energy is dissipating. So this machine is impossible. There will always be some loss or some form of energy dissipating into other form while converting heat into work. That is why this imaginary machine is not possible, and such machine which continuously produces work by absorbing the heat is called PMM1 of first kind. Limitations of the first law of thermodynamics. The first law of thermodynamics treats work and heat interactions as an equivalent form of energy in transit. Okay, first drawback of first law of thermodynamics is the law treats both work and heat interactions as equivalent forms of energy in transit, because it is not true. Work and heat both are not equivalent form of energy. Work is considered to be high grade energy, whereas heat is considered to be low grade energy. And second one, and this law does not indicate the possibility of a process. Okay, the meaning of this drawback is the first law of thermodynamics will not indicate whether the process is possible or not. It just says that if the process occurred, then summation of heat interaction is equal to summation of work interactions. But it will not indicate whether the process itself is possible or not. Okay. Then these are two drawbacks of first law of thermodynamics. Then Joule's experiment demonstrated that energy when supplied to a system in the form of work can be completely converted into heat. You can observe here, okay, very important concept to be understood. Joule's experiment demonstrated that energy when supplied to a system in the form of work can be completely converted into heat. Okay, you can observe in this equation. Okay, if you supply work in the form of work, then that complete work can be converted into heat. But reverse of this is not possible, which means if you supply some amount of work, complete conversion of heat into work is not possible, whereas complete conversion of work into heat is possible, but complete conversion of heat into work is not possible. But first law of thermodynamics doesn't indicate that whether we are converting work into heat or heat into work. If we are converting work into heat, then first law of thermodynamics holds good. It is true. But in second case, when we are converting heat into work, then first law of thermodynamics doesn't hold good. That is the reason why this is the major drawback of first law of thermodynamics. It doesn't indicate the direction of the process, which means indicate that whether we are converting heat into work or work into heat. Okay, these are the limitations of the first law of thermodynamics. Okay, let us solve some numericals. A stationary mass of gas is compressed without friction from an initial state of 0.3 meter cube and 0.105 megapascal to a final state of 0.15 meter cube and 0.105 megapascal. The pressure remaining constant during the process. There is a transfer of 37.6 kilojoule of heat from the gas during the process. How much does the internal energy of the gas change? Okay, let us have a look at the solution. Okay, Q equal to, consider the first law of thermodynamics. We know that Q equal to delta U, change in internal energy of the system, plus work done during the process. Then rewrite the equation 1. Q1 to 2 means in the process 1 to 2. Then change in internal energy is U2 minus U1 plus work transfer during the process 1 to 2. So W1 to 2. Then W1 to 2 PdV work can be calculated using this formula. Because this is a constant pressure process, then PdV formula becomes P into V2 minus V1. Then you will get work done or work transfer during the process minus 15.75 kilojoule. Minus sign signifies that work is done on the system, whereas heat transfer is 37.6 kilojoule. Substituting the equation 1. So if you substitute values of work transfer and heat transfer in equation 1, you will get change in internal energy U2 minus U1, which is minus 21.85 kilojoule. The internal energy of the gas decreased by 21.85. This minus sign signifies that internal energy of the system is decreased by 21.85 kilojoule in the process. When a system is taken from state A to state B, as shown in the figure, along ACB, 84 kilojoule of heat flow into the system, and the system does 32 kilojoule of work. Then calculate how much will the heat flows into the system along the path ADB if the work done is 10.5 kilojoule. Then when the system is returned from B to A, along the curved path, the work done on the system is 21 kilojoule. Does the system absorb or liberate heat, and how much of the heat is absorbed or liberated? And see if UA, internal energy at state A is 0 and internal energy at state D, UD equal to 42 kilojoule. Find the heat absorbed in the process AD and DB. So you need to find out all these parameters which he has asked. Okay, you can observe the diagram here and let us go to solution. So QACD, heat transfer involved in the process A, C and B, that is 84 kilojoule he has given in the problem. Then work done during that process 32 kilojoule, that also he has given in the problem. Then we have first law of thermodynamics, heat transfer Q during the process ACD is equal to UB minus UA plus work transfer during the process ACB. Then change in internal energy during the process ACB is 52 kilojoule. Then similarly for the process heat transfer involved in the process ADB, this A and B, change in internal energy UB minus UA plus work transfer during the process ADB, which is heat transfer involved during the process ADB is 62.5 kilojoule. Then similarly heat transfer involved in the process B to A, change in internal energy during the process B to A plus work transfer during the process B to A. Then heat transfer involved in the process B to A is minus 73 kilojoule. The system liberates the heat here. Minus means system liberates the heat, which means heat is rejected by the system. So minus sign. Then finally work done during the process ABD can be split into work done during the process AB plus work done during the process DB. Okay, which is equal to work done during the process AB, because work done during the process DB is 0 because it is constant volume. Then work done during the process ABD is 10.5 kilojoule. Similarly heat transfer involved in the process AD is equal to change in internal energy in the process AD plus work transfer in this process. Then we know the change in internal energy UD minus UA. So heat transfer 10.5, which is 52.5 kilojoule. Then Heat transfer involved in the process AdB is equal to 62.5 kilojoule, which can be split into heat transfer in the process AD plus heat transfer in the process dB. So finally heat transfer in the process dB is minus 10 kilojoule, plus 10 kilojoule. So this is the solution. Let's solve next problem. A piston and cylinder machine contains a fluid system which passes through a complete cycle of 4 processes. During the cycle, the sum of all heat transfer is minus 70 kilojoule. The system completes 100 cycles per minute. Complete the following table showing the method for each item and compute the net rate of work output in kilowatt. Okay, we need to fulfill this table. Wherever the blue marks are there, no, which we need to fill, but I have already calculated, I have filled here. So wherever the red marks are there, so red, he has given the data. Wherever the empty is there, no, empty, that we need to fill. So using the given data, we need to fill. Let us go to solution. During the process A to B, for process A to B, apply first law of thermodynamics. Heat transfer involved in the process A to B is Q equal to delta E, change in internal energy plus work transfer. In the process A to B, heat transfer is 0, is given, then change in internal energy is minus 2170 kilojoule per minute. Then for process B to C, apply first law of thermodynamics, and in the process B to C, work transfer is 0, then change in energy or internal energy is 21,000 kilojoule per minute. Then for process C to D, apply first law of thermodynamics, then calculate work transfer. Then process D to A, summation of, for process B to A, summation of heat transfer during the cycle is equal to minus 170 kilojoule. The system completes 100 cycles per minute. Then summation of all the heat transfer is Q A to B plus Q to B to C plus Q C to D plus Q D to A. All this is equal to 17,000 kilojoule, because it is for 100. Then Q A to B is 0, B to C 21,000, C to D 2,100. Then Q D to A, heat transfer in the process D to A is minus 35,900 kilojoule per minute. Okay, this is the solution. Using all the data, we can fill up the previous table. Okay, till now we have seen that, or we have applied first law of thermodynamics to closed system, and we have solved some problems. And now we will apply first law of thermodynamics to flow process or control volume or open system. Okay, so till now we had a discussion on application of first law of thermodynamics to closed system. Now we will apply this to open system or flow process. So before that, let us understand the concept of control volume and control surfaces. For the analysis of open system, attention is focused upon a certain fixed region in a space, because the system is open. That is why for the analysis of open system, attention is focused upon a certain fixed region in a space is called control volume. In the figure you can observe, and the control volume is bounded by a surface which is called control surface. For example, in many engineering applications we will come across many open systems. For example, air compressor we are seeing in the in this figure is an example for open system. So for this process, the surface which is bounded here is control surface, and inside this is control volume. So this is how we will treat the open system to apply the first law of thermodynamics. Then flow process or flow. What is the mean by flow processes or simply a flow? It constitutes an open system in which fluid enters and leaves the control system. Simple definition for a flow process or flow can be defined as: it constitutes or flow process or flow constitutes an open system in which fluid enters and leaves the control volume. So this is how we need to understand the concept of control volume and control surfaces and the meaning of flow to apply first law of thermodynamics to open system. Types of flow processes or flow. There are two types of flow processes we will come across: steady flow process and unsteady flow process. Steady flow process is the flow in which fluid properties such as pressure, temperature, density, velocity, etc. remains constant with respect to time. For steady flow process, all these fluid properties, pressure, temperature, density, velocity, will never change with respect to time. Whereas in unsteady flow processes, fluid properties like pressure, temperature, density, velocity will change as time changes. So that is why the name is unsteady flow processes. Unsteady means something which changes here. Properties of the fluid will be changing as time changes. Whereas in steady flow processes, all these fluid properties will be constant with respect to time.